parameters. So the standard way to do it is called dummy variables encoding. So let me show how it works. Okay, so here we have three options for this categorical variable, like C, Q, S, and we can transform this one categorical variable to three columns, right? In each time, only one of these columns can be true, and the rest of them are false, which is obviously an indicator of this particular categorical feature. Like here is for passenger 1 is S, and this guy is true, and the rest of 2 are false, and so on and so on. So it's called dummy encoding or one-hot encoding, which is maybe more intuitive because here only one element can, like fire, can be non-zero. Okay, this is one-hot encoding. So maybe some of you noticed some problem here. Are there any problems with one-hot encoding? How do you think?
We have extra columns.
Sorry?
We have extra columns. Instead of one value, we have the vector of 3 each.
Well, yeah, this is obvious. So if you have a huge dimensionality, it is called cardinality. For categorical feature, it is called cardinality, right? Your dimensionality of features, it will be the same. It will be large. So this is obvious. Like, does anybody see another problem?
Also, we can drop one of the column because if we have false, it is obviously we have true in third column. So we have one redundant column.
Yes, indeed. Yes, so there is dependency between them, and if you know like any two values, any two columns, we can find out the value of the third one. Yeah, and in standard encoders, like there is always an option. You can drop the one redundant value. So in this simple case, let's do it. Let's drop S. Yeah, so we are dropping it, and then we are joining our main data frame with this dummies with one-hot encoding. Okay. Yeah, and finally we are dropping the original column because it was a string. We don't like strings. Okay, that's it. Let's move next. What is it here? Yeah, so this is a visualization how the probability of surviving changes with the passenger class. So obviously the dependency, this is anti-correlation. The probability of survival is highest in the first class, is lowest in the third class. So yeah, this is quite interesting example. So how to work with the passenger class? You can think about it as an integer, right, or categorical value. So in general case, this dependency might not be monotonic versus class. The classes, the passenger classes, they can be called, A, B, C, D, or whatever. That could be A1, B20. So in general case, it is better to transform passenger class also to dummies, to do one-hot encoding. Yes, in this particular case, it is fine to work with it as a real value because the dependency is very obvious, but yeah, we will have like more general case in mind and do the same for class, for passenger class. Transform it to dummies in one-hot encoding. Okay, let's move next. Let's examine fare variable. This price of ticket. What do we have here? Let me see. So I think the first one, it is a histogram of fares, right? There is always peak in some region of small fares. Yeah, and the second one, it is a box plot. It is a distribution. We have two discrete options, survived and not survived, and we can get distribution of a real value, okay, for these two discrete choices. So these boxes and lines, they show, if I remember it correctly, was something like standard deviations and quantiles, something like this. Okay. For those who survive, this is a typically higher fares. Okay, let's move next. We have age. We have some couple of plots for how age is distributed, like histograms, frequencies. So yeah, we had also one problem that in age column we have also missing values, right? Yeah, 177 nonce in age. So we need to solve it somehow. Let's do it. Here is my solution. So we are calculating for the age. We take on all present entries and we calculate mean, standard deviation, and we replace all missing ages with random variables which mimic the real distribution of ages. Okay, like here is old ages, new ages, like the distribution is more or less the same. Okay, here is just a nice example of what CR-plot can do. This is like two histograms which are smoothed for histogram for each option of categorical variables, survive, not survive. These distributions are slightly different. Yeah, in the bottom there is probability of survival versus age. Yeah, here age is discrete. Yeah, so the first one was the facet grid. The second one was the bar plot. Well, this is just an illustration of what we can do with CR-plot. Okay, I think there is, yeah, there are several transformations. So instead of having two columns for parents and children and sibling and spouse, we have only one column which represents if passenger had a family member abroad or not. So meaning if having any family member, whether parent, brother, and so on, it actually increases chances of survival. Okay. So we are creating like one joint feature which is called family. It is number of parents, children, siblings, spouse, all together. Yeah, and we make it like binary. So if it is 0 or non-zero. Okay, now let's let's study what's going on, and what we can conclude that most of passengers traveled alone, without family, but the probability of survival is much higher with a family. So this is lesson for everybody. You should have a family and travel only with a family. Okay, the probability of survival increases by 20%. Okay, the last transformation which we will do. So yeah, actually all this transformation, they increase the quality of classification a little bit. Like in the end, we will do a classifier which will predict us whether this person like survived, predict if he survived, if it will survive. Of course, we know what happened, who survived or who not, but we like pretend that we don't know it and build a classifier. And this feature engineering which actually helps. So the last thing what we are doing, we have a sex variable, and we join information from age and sex, and create like a new field child. Because if person is young, it doesn't matter the sex, it doesn't matter. Okay. So yeah, this code does it. I don't dive into details because the stuff is more or less the same. Child, it is equal age less than 16. And we are creating a new categorical variable person, which can be either male, female, or child. And now we get this count clause, right? This counts for male, female, and child, and the probability of survival, which is highest for females, childs, and very, very low for males. Okay. Well, it's time for another task. Oops, solution. So yeah, this task is quite short. Please study if the distribution of age is similar for man and woman, and please compare age distributions for all three classes. Okay. Something like 5 minutes will be enough.